So we know what our simulation output should look like because it's such a simple scenario. Now we have to go and build our solver to get that. We're going to start with Euler's method. And Euler's method was this basic formula. So this is our old y, or new y, sorry, new y, old y. This is delta y, or dy dt times delta t. What we need to do now, though, is basically put a vector on this. So my y is now a w. So w has two things in it. And this is my new position and new velocity. So this is new position, new position and velocity, and we're going to stack them up as a column vector. It's going to equal our old position and velocity. We're not making this stuff out of new cloth here. Plus, and here's what we get. This is going to be W1 prime, W2 prime, or f of TWI here, TIWI, times delta t. So what we have to worry about now that we didn't have to worry so much about before is what's a vector, what's a scalar. If I'm talking about position velocity, that's always going to be a vector. My old position velocity is a vector. The derivative, which is dw dt, is going to be a vector of the two derivatives. In fact, we have that on the last page. This is our vector of two derivatives. This is d dt of w1 and w2. So it's a vector as well. The derivative, I have two things to take the derivative of, so we'll get a vector there. And the only thing that's still left as a scalar is time. So we're going to need to take advantage of that structure when we go to write our code to solve this. Hoyne's updating formula has a similar kind of arrangement, but it's basically the same thing. We'll see that more in action. What I want to focus on now is the input-output. So we know what we're going to have as input. As the output, we're going to get t, which is going to be a vector of time values, starting at 0, going up by delta t every time, whatever that is, and down to some t end value. Matching with that is our what's my position, what's my velocity. How many columns, let's go with columns. How many columns should this w have when we're done? Number of elements in T. That'll be the number of rows. So this guy will have a one-to-one mapping row-wise. So same number of rows as T. That's perfect. How about columns, though? Yeah. 4 and Y. What is our W this time now? How many things are in W? Just 2 this time. For the pendulum with X, Y, and the roller coaster will have 4 because you defined it. This is all about what you defined as your W. For today, for this system, there's only 2 variables we need in W, position, velocity. So our W that we get back here needs to track position and velocity at each time. So it'll just have 2 columns because W, our vector here, has just W1, W2. So what we want to build is at time 0, I need my current position velocity. And then I'm going to go down 1 time, and then I'm going to say, what's my new position and velocity? And then the next time, what's my new position and velocity? We could draw a graph. Hey, my position was initially 4, and then it went down and down, and then went up and up, and then went down and down. We should be able to simulate that by doing little incremental steps and connecting those dots with straight lines. We're into code now. So there's a bunch of verbiage here, but the take-home message is when we did the temperature model, we wrote it as a little ampersand function of t and y. That was fantastic because this was simple. It was easy. There's one value, y and t. Then I calculated one derivative value. It's not going to be quite so easy, and we didn't do this when we did the pendulum. Anything that's more complicated than that, we should probably put in a separate .m file. So we're going to need that. We're going to need a few pieces here. We'll take a look at each one of them individually. So first off, file number 9.2. So notice, our initial values, because W has 2 things in it, the initial W has to have 2 things in it, position and velocity. Where am I starting? What's my initial position? What's my initial speed? 0. Then we define our time interval. That's fine. We define our constants. This is all definition stuff. Then we get to some undetermined things like our spring differential equation and this solver that we're going to get into next. One of the things we're going to need is our differential equation. Notice this is going to mirror exactly what we write on paper. The rule for how this system works is a differential equation based on a spring. What do I need to know about that to make it work? Well, we go back to our on-paper stuff. Go back, go back, go back, go back, go back. All right. So this was our system of equations. We are going to translate this into Matlab. We are not going to do anything to it because this does exactly what I want it to do. If you tell me what W is, W1 and W2, you can tell me the rate of change of each one of them or the slopes on their graphs. We are just going to formalize that. We're going to make this a column vector. That's the way Matlab usually does it for the derivatives. And actually, we're going to do this straight out of the what we just saw on the page there. So write using the equations from the page. So in the page, we had dw dt sub 1, but now it's bracket 1 because it's the first element. And literally, it is W2. So that comes exactly from this, only in MATLAB-ese. The derivative of W1 is W2. Bracket 1, bracket 2 to make it elements of a vector. The second one is the second element of our derivative, which is this derivative of the second W, is minus k over m times W1. That is it. Copying the math, recognizing that subscript 1 usually means the first element, subscript 2 means the second. That's what we get for our differential equation. All right. So what we get here is, we remember what our input arguments are here. We had t, w, k, and m. But solvers in MATLAB assume that there are exactly two inputs to a differential equation. And those two inputs are t and w, t and y, t and whatever the state variable is. So that's why we have this little bridge function here. Spring takes four things in, t, w, k, and m. We can't use that with our solver. So we make this little juncture function called f, which is a function of t and w, function of t and w. The t and the w are going to go straight in. So if someone tells me a t and w, I'll put them in as the first and the second ones for our differential equation. But I've already hardwired values for k and m, so I can tack them in here as well. Those will be hardwired just because of the syntax that they were defined earlier. The t and the w are things that I can provide later, and they'll be passed in as the first two inputs. OK. Once we're done that, we can actually build everything else the same way. If we're going to solve a differential equation, we need to have our function f. We need to have our time span, which was 0 to tn, or t, I call it t0? I call it t0. t0 to tn, we made that a vector just, again, to match what MATLAB does for some of its solvers. We give it the initial value, and we give it the number of intervals. So the way to read this is, I would like you to simulate or solve my equation. What's my equation? My equation is f, which is a function of t and w. It's really the spring differential equation in disguise, though, so it's simulating the spring stuff. Over this time interval is a vector with this initial value and this number of intervals. So with all that information, I know where I'm starting. I know the rule for updating. I should be able to simulate for the time span that's given there. Now we need to build this still. Let's go back to where we were in the notes. What we're going to do now is modify what we already have, which is our ODE Euler. So I'm just going to open up ODE Euler here, which had a whole bunch of comments. But the key thing was those two formulas we talked about just earlier today. Hey, my t is going to be, my new t is my old t plus delta t. My new y is my old y plus the slope times delta t, or the rate of change times delta t. And we're just going to tweak this to make it work with vectors. So I'm going to save this as ODE Euler system, I think. Let me just confirm. Yeah, system. Keep it consistent. And then we just look at what we need to change to make this work for a vector. Yeah, I'm going to change all the w's to make it a little more obvious. So I'm going to change that to w naught, and then I'm going to press Shift-Enter to change them all. Every y, I'm going to change it to a w. I'm going to take advantage of MATLAB offering to change all of them for me. That's fantastic. OK. The t values don't change much in there. At the end of the day, the ti plus 1 is still going to be the same ti plus delta t. That does not change at all. My time is going up by a fixed amount. It's not a vector. It's just a scalar. So when I get to that line in this part here, it's the same. This next line, the W line, is where things get more complicated. W is now going to be a vector, sorry, a matrix. Matrix with 2 columns and lots of rows. As we go through time, am I filling in rows or am I filling in columns? Let's go back to the picture. We have to think about what you want to build. Is filling in as we go on in time down rows or columns? Rows, right. We're filling in as we go. W is the match set of that where every row matches the time. So what we're going to do is fill in the first row, then advance time, fill in the next row, advance time, fill in the next row. So we have to think about that. I need to fill in the rows. When we look at the code here, right now it's just a vector, so row column doesn't matter. But I want it to be row I plus 1. I'm going to be at row I, filling in the next row I plus 1. But we want to fill in all the columns at once. So that's the minor change. We're going to say W, the next row, all the columns. Our old W is the last row, the row before that, all the columns. So again, what we're trying to capture is the updating function. There we go. Wi plus 1 is a vector, but it's a row vector. So we're going to get all of that row, all the columns, is going to be our Wi, so the ith row, all the columns, plus, now we have this stuff here to work out. F of ti is fine, but what we're going to put in is the ith row. So basically, we're doing this, turning it into a vector thing, which in Matlab means grab a row or a column of a matrix. So each row is going to be the vector we're talking about in our calculations. And it should be consistent. It's always row I plus 1, row I, row I. And honestly, that's the majority of it. I think we'll try running it and see what breaks. I think that'll be more informative than trying to eyeball it off the top. So let's try to run it. And it's not vector, it's system. Sorry, system. We have to name the function the same way we did ourselves. All right. All right, so we get a bunch of errors, which is not a huge shock at this stage. So what it asks you to do here is actually interpret these errors and make sure you understand why MATLAB is legitimately complaining about what we've done here. So the first, again, is a reminder of how to debug these things or how to read this error. My main function called my Euler system, and that's where the error is. So I'm going to click on the link. I think the mistake is in Euler. So we're going to click on that and see what we get back. OK. What is wrong with W1 equals W0? Perfect. You're trying to equate one entry. W1 is one number. W0 has 2 very specific numbers in it right now. What are those 2 numbers? 4 and 0, right. So I'm saying 4, 0 equals a number. So what did we really mean here? Well, we meant, put W0 in the first row, right? W has, let's go back to the picture. There we go. The W0 should be that first row of this matrix here. This should be W0, which is position and velocity, which is 4, 0, which all makes sense in that context. OK, so we're going to save back to our main script and run her again. And OK, it's still unhappy with that line. OK. Dimensions don't match. That's interesting. Why do you think it's complaining about that? What else could be going wrong besides it not being a scalar now? Ah, right. What did we actually create W as? If we go back to the top, W only has one column. So we said put it all in the one column. So we have to tweak that. How many columns should we use? Well, the temptation is to put a 2 in here. But of course, our system today has 2 things. Our system on Monday had 4 variables. Last week had 4 variables. So we don't want to hardwire this. So we're going to do exactly what Matlab does. Matlab uses your initial condition. You, the user, provide this to say, well, if you put 2 numbers in W0, there must be 2 variables because the initial value has to have all the variables defined. So what they do here is just say, the number of variables is going to be however many initial conditions you gave me. We are giving it 4, 0 That's two numbers, so length of that vector is going to be 2, and that'll build a 2-column system W. We'll try that. Now we're in business. We got further now. Okay. So just to note that change, instead of hardwiring it to 1 or 2 columns, we say how many variables are there? The length of that initial vector gives us how many variables are in play. And then we get to the fun stuff. So down here, there's a problem. Matrix dimensions must agree. Does anyone have a hypothesis here? We're filling in rows of W. We're going down row, 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 row. We're using our spring differential equation to be this F here is really being called, or is really calling, the spring differential equation. If you look at those two things, filling in rows and our spring differential equation, is there a mismatch somehow? Actually, honestly, the output here, if I was going to debug this myself, which we might as well do right now, is I would just take all this stuff out and just print it. So put it in here without a semicolon. We'll try to run it. And of course, we can't run a function. So we go back to our main script and we run that. And there we go. This is what our spring differential equation is giving us back. It's velocity acceleration. And here's where we're trying to use it. We're trying to say this row is my old row plus this times delta t. F is in what form? It's right there. It's in a column, right. So what we're asking Matlab to do, and it's legitimately upset with us, I know this is not the most exciting stuff in the world, but this is the crap that has to get fixed, is we're trying to fill in a row here, and we're saying, oh, yeah, take this and add it to this, 0 minus 12. And it's saying, completely legitimately, those, when you try to add two things, those dimensions had better be the same, or I can't do what you're talking about, because it makes no sense. So the problem is the matrix dimensions. One's a row vector, one's a column vector. They don't agree. It yells at us, and we have to fix it. So how would we fix that? We don't want to change our differential equation. It turns out it's easier to work with column vectors there. But how can we change this calculation so that it does work out with everything being a row? How can I make everything to be a row? Put an apostrophe at the end, exactly. This is a perfectly good column vector. If I want it to be a perfectly good row vector, I just take the transpose of it. So I just put literally one fix of an apostrophe at the end, little quote there. That's the transpose. And that should fix everything. We'll go back to our main script. We'll run it. And things are running. I'm just going to get rid of my debugging line here. But as a general theme, what I'd say is if you're getting an error, just try to piece out what's happening. What are the inputs just before the line that's causing the problem? Here, the line was the blah plus blah. OK, what does it think it's adding? And are those the same things I think it's adding? Take a look at them explicitly and see what you can fix. All right. Now, the next thing we're going to do is plot t against w, because t and w are the simulation results. So against time, what are my position and velocities? And there we go. You'll notice one of these values here is around 4. Let's try that way. There we go. There's our initial position of 4. Initial velocity is 0. Run that again just so we get the big picture. Cool. So that's what the graph would look like. I should emphasize that we don't actually get this. We're inferring that. What we actually get back are a sequence of dots. Right? We're estimating at points, and then we're hoping that by connecting them by straight lines, we actually get something meaningful. But that's it. We have generated a simulator for a second order system now, second degree.